We have a large minus 20 Celsius ice cube. Ooh, that's some cold stuff. It is dropped into a super insulated container holding a small amount of 5 Celsius water. The container is sealed. 10 minutes later, is it possible the temperature of the ice cube is colder than minus 20 C? What do you think about this? A lot of people saying B. And I like that because the answer is B. You cannot get the ice cube colder. This is a fundamental aspect of thermodynamics and is what we call the second law of thermodynamics. And in this lecture today, I'm going to go over a lot of different versions of the second law, but you can put it that way. Because there's a lot of ways you can state it. There is sort of a universal statement you can make, except it's a little abstract. Let me put it that way. And there is a lot of equivalent second law statements. And I actually find it more helpful to not think about the one abstraction that is usually associated with the second law, but to look at a lot of effectively equivalent statements, because ultimately you need to understand the process, then understand some obscure, abstraction of it. And the idea is basically this. If you bring things that are not in a thermal equilibrium, and remember what that means. It means they're not at the same temperature. There will be a heat transfer between them. The heat transfer, however, always happens from hot to cold. Okay? Hot to cold. So that means that warm water is going to start to heat up the ice. Now, we weren't told any quantities here, so who knows what's happening. We have a few scenarios, right? If there's not a lot of water, well, then the ice will heat up a little bit, and the water will drop down to some lower temperature, right? If there's a lot of water, there could be enough energy to melt the ice and bring the system to an equilibrium temperature. It's possible, certainly possible. But what has to happen here is, if you don't have a lot of water, well, yeah, the water's going to cool down to probably 0, and the ice may heat up. It's possible the ice grows a little bit in mass. That's a possibility, I guess. So, anyway. I mean, again, it depends on the quantities. I'll just say that. Yeah, but without any other knowledge, then we can say no. Okay, now, this process, though, is what we call an irreversible process, meaning it cannot spontaneously go in the other direction. If I want to make the ice cooler than minus 20, I can do that, but it's going to require me to do something to the system that ultimately will result in a lot more energy being used in the process there. And so the statement of heat transfer from hot to cold, irreversible processes, these all kind of go hand in hand with each other. Okay. So, another question for you here. Which statement about these two thermodynamic processes is correct? So in one case, we have ice at 0 and liquid water at 0. In the other case, we have some different temperatures going on. So let me know what you think about this. B's and C's. A lot of C's, though. A lot of C's, and I'm happy to hear the C's, or see them. I didn't hear anything. I saw them. The upper one is reversible, and the lower one is irreversible. Okay, so what are we saying here? If things are in a thermal equilibrium, okay, i.e., same temperature, the processes are considered reversible. We can bring this system here with the addition of heat. We can melt the ice and turn it to liquid water and leave it at 0. We can also extract heat out of this and bring the liquid water back to ice. We can go back and forth. That's perfectly allowed. Okay. What down here, this is not allowed. This is an irreversible process because once the ice is melted and it is brought to 20 Celsius, there's no spontaneous way that you can easily get back there. You usually have to perform some extra amount of work or something to achieve that. Okay, so what you should equate in this is that things at the same temperature, meaning thermal equilibrium, can be reversible. Those processes can be reversible, but the other ones, physics does not allow them to be reversible, so we call them irreversible. Okay, great. Oh, well, this is what I just said here. All right. Is there anything you have to add to this? I don't believe so. Right. Yeah. So that's the thing about the reversible process here, is that the changes that happen can be these infinitesimal changes. This kind of goes back to an earlier concept that we very briefly discussed called quasi-static processes, where little tiny changes are done that allow the system to always maintain a thermal equilibrium, but a change can occur overall. And that's allowable. You don't need to do any special amount of work for that. If you just do small little changes, you can achieve this reversible process. Whereas you can't do that in an irreversible process. You can't perform a little action and get it back to the original state, because it would require ultimately heat to flow from, the heat normally flows from hot to cold. You have to reverse that, and it's not something that you can do because the metal box was at 70, now it's at 40. Well, you're not going to get that metal box back up to 70 unless you have some external thing to do that. That energy cannot be extracted purely from the water that now has attained this higher temperature. All right. But this one is reversible because the temperature is the same. That's the idea. Okay. My nose is so itchy. Oh, ugh, can't stand it. All right, so this is an interesting little thought experiment here on equilibrium. So the figure that we have here has these two boxes, right? And we have balls in them. And every second, what happens is a ball gets transferred. And it's at random. Just randomly, a ball gets transferred back and forth, back and forth, back and forth. And the idea is that, if we had a process like that, what we would expect to happen, okay? What will likely happen is that when we come back, there will be an even distribution of balls, okay? It would be very strange if we came back and one box was completely filled, because that would require, constantly randomly choosing balls from the second box, and it goes to, say, the first box. And while statistically possible, right, when we try to translate this into a physical system, we find that the statistical anomaly is basically an impossibility. And it has a lot to do with the fact that the balls will interact with each other. Here, the balls aren't interacting with each other. So statistically speaking, if we had 100 balls and 100 balls, is it possible that every time you select a random ball, you select one from box 2? Sure. If the balls interact in some way, though, and that influences how they're selected, well, that's a different story now. And so this drift that we talk about is also an irreversible process as well. You will eventually tend towards a state where there's an equal amount of balls in either one. And that's just due to random statistics here. Now, for gases, it becomes more complicated because there's interactions and other things that take place. And everything is ultimately obeying the second law. So, all right. So here's a good example of more reversible, irreversible processes. So in the example here, we have these two objects. Maybe they're charges. We can say they're charges, maybe. And they're like charges, so they're shot at each other, and they're going to deflect away. Right? So they do that. Now, the before picture here, if we go forward of this, going back, it's certainly possible here because it's single interaction between two objects, right? And I mean, if this really is like electricity, say it's an electrical interaction here, you have conservative forces, no energy is being dissipated away. So that's certainly possible to do there. Okay. This one here is not going to happen because we do have dissipated forces here. The car smashes into the wall. Well, are you ever going to have a case where a car can back up and fix itself? No. I mean, same thing. If you have a glass here, take like a wine glass, right? Drop it, and it shatters. Is there any possibility that there'll be a process spontaneously that will put the glass back together and it will become a cup again? No, because there's energy that was dissipated, taken away. And this is really at the core of all this, is that there are a lot of processes that are not conservative processes, that don't retain the energy in the system. It gets expelled in other ways. And another statement of the second law is you can't just decide to pick up all the pieces and put everything back together and have everything to be the same. That will not happen spontaneously. You can do something like that. I could repair the glass, but I'm doing a lot of work to do that. And you have to put in a lot of extra energy to get that done. So it's not what we refer to as being properly reversible. Okay. All right, so let's start looking at this, though, from a less abstract view. Let's start looking at it from the perspective of thermodynamic processes, because that's what we're doing here. We're talking about thermodynamics, and we're talking about how to apply these concepts. So I have a question for you here. We have a PV diagram. We have a process that is broken up into 3 steps. We have an isochronic process, we have an isothermal process, and we have an isobaric process. And I just ruined it. You didn't see that. You didn't see anything. You didn't see. There wasn't an. Yeah. Anyway. All right. What do you think's going on here? Which of the processes in the cycle could be reversible? So many people in the chat here. B. Well, hope you're saying B because you know it's B, not because I ruined it. But. Yeah, the isothermal there you go. Isothermal process is reversible because the temperature is not being changed. This all is going to come down to if a system changes temperature, there's a particular natural flow of energy. Okay. So let's move on. All right, so let's start looking at some scenarios. When we talk about these scenarios and we look at systems where energy is transferred between them, we talk about energy reservoirs, right? Energy reservoirs. And that's where energy could come from and where energy leaves. Okay, so in the example here, we have some strange example where we have this copper bar placed above a fire, and it will heat up the bar due to conduction. There will be energy that will transfer through the bar, and then it will eventually hit an area that is, well, I mean, you don't really need to have the ice there, I suppose. The idea is that the bar gets hotter and the energy flows to the right-hand side. There's never a situation where you do this process and heat flows to the left and somehow the bar ends up hotter than it would be if it's being lit by the fire. That's not something you can do. So we separate these things into what we call a hot reservoir, which is simply at a higher temperature, and a cold reservoir, which is at a lower temperature. That's all the requirements. Let me just say one thing about this to warn you. You don't necessarily talk about reservoirs in terms of extracting energy out and dumping energy away, although that is true most of the time. Okay, not all the time is that taking place. For example, refrigerators work the opposite way. Okay, we're dumping energy out of a hot reservoir, and we're taking energy from a cold reservoir. That's a different scenario. But ultimately, there's something at a higher temperature and something at a lower temperature. And that is what we care about when we talk about these reservoirs. But do avoid thinking about this as extracting energy out of here and putting energy into there. That's true many times, not in all situations, though. Okay. All right. So here is some other statements of the second law of thermodynamics. So, it is impossible for a system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same state at which it began. So that's another statement here. Ultimately, all of these things are what we call isomorphic, right? What they mean is, it's a different way to think about these, but when you boil it down to the fundamentals, they all really are saying the same thing. But this is another really interesting statement about that. Now, the fact that you can't have heat flow spontaneously from a hot reservoir to a cold reservoir also implies this other statement here, that you cannot take heat out of a system and have all of that energy being turned into work with no other energy being lost or used up in any way, and the system remains the same. Okay? And a similar statement is it impossible for any process to have as its sole result the transfer of heat from a colder to a hotter body? Well, that's kind of that's the refrigerator statement of it, but it is equivalent to the engine statement, which is the one up top. Okay, so let's look into this because it may not be entirely clear why this is the case, right? So let's do that. Okay, so on the left here, we have heat flowing from hot to cold. Fantastic. Easy done. Happens all the time. No big deal. The one on the right, though, is not something that you can do. You can't have the heat flow from cold to hot spontaneously by itself. Now, these diagrams, you're going to start to see these diagrams a bit more. This is a way we talk about basic engines and how heat is moved in them, and we call them heat transfer diagrams. How it typically works is we have a hot reservoir and a cold reservoir, and we have a system. The system is maintained in the region between them. And so in this example here, we don't really have any kind of system. We just have a means that connect the reservoirs together. The one on the left is allowed. The one on the right is not allowed. Wait, give me 1 minute here because I think something happened here. Give me 1 minute. Sorry. I'll be right back. Okay, never mind. It was getting weirdly hot in this room, and I thought that the breakers tripped on my AC, but they didn't. It's just 4 o'clock when it's the hottest that it gets, and the walls are leaking heat like crazy. It's the high today. It's not 85. What? What? It's 85? No, it's not 85. What? I don't believe it. Anyway, okay, that's very strange. Doesn't seem like that at all. It's been very hot. Yeah, I know. Like, what's up with that? 80? No, it's not 85. Am I in the wrong area? No, it is 85. What? Whatever. Whatever. All right. What did I do? What button did I hit here? Sorry. It's nice out. I want to be outside. Oh, well. Can't do it. Stuck in here till like 9 p.m. Oh, my goodness. Sorry. I'm hitting the wrong buttons here. I cut my fingers accidentally. See these? Cut this. So I can't use this on my mouse. I have to use my index finger. I cut them hard. I tried to open up a container of butter, if you can believe that. That butter was brutal. Anyway, sorry. All right, so here's what we're really interested in doing, though. We can't take a bunch of heat and purely convert it into some usable work. Meaning we can't extract energy out of a heat reservoir and perfectly take that energy and put it somewhere else that can achieve something useful. That's what we refer to as the conversion of work into heat. Okay, it's not something that you can very easily do. Now, there is one way that you can do this very easily. You can do work purely and transfer energy to a cold reservoir. It's not a very useful thing to do because, as the example shows, you can rub your hands together, right? Now, that is not necessarily heat from a hot reservoir. That's just pure work being done. And the fact that my hand heats up here is not due to the fact that I'm just in contact with something. Okay? It's due to the fact that I've performed work. So this is okay. This is fine. You could do that. It happens all the time. This is what's called friction, right? That's no big deal. Except that's not something that is useful. It's not useful to do this. Okay? Because where does the energy go? Well, it's not harnessed really in any proper way. It's just things heat up. Okay, fine, whatever. Now, transferring heat purely into work, though, this process is what we would call a perfect engine. You can't do that. You can't have a perfect engine. Okay, you can't take all of that energy. Let me give you an example of this, right? A car. I don't like cars. I don't know much about cars. Not a big car fan myself. Okay. But think about this. If you know anything about cars. When you have your normal cycle in a standard automobile, right? You insert you insert your aerated fuel, right, in the cylinders. Spark plug goes off, ignites the gas, the piston's pushed out, massive expansion, right? And then that piston eventually comes back and you have exhaust. So my statement here about the perfect engine is a car would be a perfect engine if that exhaust didn't exist, right? Because when you have that exhaust, is that hot? Yeah. Say it's not even hot. Say it's, room temperature. It still has energy associated with it. So there's no way you can make a car where you can input fuel into the cylinders, combust it, and there's no exhaust, right? There's nothing that's given off. That's not possible to do that because there is a medium, right? There's a medium that performs this work, and that medium does take some of the energy with it. So you can't do this right here, okay? The way you would complete this diagram here is to put another smaller, if the width of this, branch down here was proportional to the amount of energy, we might put a smaller width going down. That's the cold reservoir, where some of the energy is done with work and some of it is done to the cold reservoir. That's allowable because that's a natural process that can take place. But something like this can't be done. And any process you have where you take energy from a hot reservoir and you want to perform work, you have to discard something. And in fact, we're not going to get into it today, but in the lecture on Monday, we're going to look at what is the most efficient way you can do it. Because the reality is you can't do it. It violates the second law of thermodynamics. So the next question you might ask is, well, what's the best that I can do? And the best that you can do is what's known as a Carnot engine. But that's Monday. So let's keep going. All right. So we're going to first look at heat engines. Heat engines are one where you start from the hot reservoir, you extract energy out of it, work is being done, some energy is expelled out to the cold reservoir. As I mentioned, the example for the automobile, that's basically what an automobile is. It's a heat engine at its in its essence here. Okay. All right. This example here, this is another great example. This is a steam turbine, and the idea is that you can heat the steam that can provide work done on a turbine, right? And then the steam is condensed and pumped back into the boiler to be heated again. That's the cold reservoir. The spinning of the turbine is the work being done. But there's no way you could heat up the steam. It spins the turbine and there's nothing discarded. Like, that would mean that somehow your water, if you could extract all of the energy out of it, well, your water would be at a temperature of 0, right? And you can't do that. So, so there's a certain percentage of that heat in the steam that can be put into spinning the turbine, and the other of it is extracted to the cold reservoir. Okay. So, in a standard cyclic process for a heat engine, because all engines are a cyclic process. I mean, a one-cycle engine's not very useful. You want engines are designed to be run repeatedly. They have a cycle associated with them. And you can always break down these engines to their fundamentals. And that's really what we're doing in 211. We're breaking down things to their fundamentals. We're going to learn the basic principles. If a lot of you are moving on and you're going to be engineers, you'll be revisiting these ideas in your classes, and hopefully you learn these core ideas of efficiency and work, and then you can start to apply them to real things. We do a little bit of application, but the focus here is mostly on the core concepts and the fundamentals here. So whatever the heat engine is, we can break it down into, we have a hot reservoir, work's performed, the rest of the energy is expelled out of the cold reservoir. There is a net amount of heat, okay, that is being used here. So we subtract the heat extracted from the hot reservoir, from the cold reservoir, that results in some net heat, and that's equal to the work that's being used to do, the energy that's being used to do some kind of useful work. So that's a basic heat engine right there. Some energy comes out of the hot reservoir, some is put in to work, some is put into the cold reservoir. We go from there. So we can talk about the efficiency of this as how much energy can we extract from that hot reservoir, and what percentage can be converted to work and what percentage can be converted to heat. So our definition here is this. The thermal efficiency of an engine is going to be a ratio. It's the work that was done by the engine compared to how much energy was available in that particular cycle. So this is like a percentage in a way, right? Based on our definition for work, though, that's going to be, we can rearrange things here. So if I go back, we can rearrange things here with the amount of work that's being done, and we can turn this into 1 plus QC over QH, okay? Now, be careful with this term here, because the idea is that this QC, sometimes there's a couple different conventions here. I like the one that's on the right here. I like to keep things all positive and realize that this is a difference. So this middle term here, this middle expression, you'll see this in your textbook. But I'm not a big fan of this because it kind of assumes that you put in your QC as negative because it's being expelled. Kind of don't like that. I kind of like keeping everything positive and considering if you're adding or adding subtractants because of what you're doing with the energy. So the last expression here, well, honestly, the first and the last expressions are really the nicer things you want to see here. Efficiencies are rather low for things, though. They can be anywhere between 10 to 50%. There is an optimal efficiency, and again, that's a Monday discussion, so we're not going to do that today. All right. So, question for you: what is the efficiency of this heat engine? So do the math there and let me know what you think. A lot of people saying C. I like C. So you can base this on work over the hot reservoir energy. Every cycle takes out 100 joules. 40 is used for work and 60 are discarded. Great. That means the engine is 40% efficient because it can use 40% of the amount of energy to do something useful. All right, simple enough, right? Don't worry, I'll make it harder. I always do. Let's rank the following heat engines in order from highest to lowest thermal efficiency. So I don't want you to chime in on this. I'm going to work it out with you here. So we want to try to work out this stuff as much as we can. All right, let's go through each one and let's calculate these efficiencies. An engine in one cycle absorbs 2,500 heat and rejects a ton of it. Oh my goodness. What kind of engine's this? This is garbage, right? Let's calculate it though. So the expression that I would use to do this part would be 1 minus 225, which is the cold reservoir, to 2511. I'm not even going to work it out. It's pathetically low. How about that? Pathetically low. I don't know what number that is. I'm not even going to bother to work it out though. That's just sad. An engine in one cycle absorbs 50,000 joules of heat and does 4,000 joules of work. Oh, well that's nice. The efficiency is going to be the work over the hot reservoir energy, which will be 4,000 divided by 50,000. And that sounds like 0.08. Is that right? Am I doing that math in my head correctly? Okay. You know what? That's pretty awful too. I guess I better do the other one. Oh, here's my calculator. All right, 2250, 25. Okay, well, this is pathetically low, but it's still 10%. It's still 10% though. All right. I won't say it's pathetically low. I'm so sorry. I don't want to disparage these heat engines. They're doing their best, man. They're trying. So 10%. I'm going to convert these to percents, as you can see. 8%. I mean, they're decimals, right? But I'm just going to convert them to percents. Okay. Heat engine in one cycle does 800 joules of work. That's nice. And rejects, ooh, it's a lot. So guess what? The QH in this example is 6,400. That's our QH. Because we had to add together the work in the cold reservoir. All right, so that means the efficiency here, ooh, this looks like a good efficiency, right? Work over the hot reservoir, that's 1/8, which is like around, what, 12.5%? So it looks to me that C is the best, followed by A, not so pathetic, and then B is the real sad one. B is the sad one. Okay, is there any questions about how we calculated these efficiencies, calculated the heats, reservoirs, things like that?
Dr. McGovern?
Yes.
So for part C, what for your QH, what numbers did you use?
Yeah, so the idea here is that, I'll back this up a little bit here. Q, the hot reservoir energy, which I'll call QH, is always going to be split up into some amount of work and some discarded energy. So the fact that we knew the work, we knew the rejected energy, which is QC, that allowed me to calculate QH. That makes sense?
Yeah.
Okay, great. All right. Any other questions?
So it's always going to be like this format. There's never going to be not like any like change in equation or anything. It's just going to be like this, or at least for calculating efficiency.
For the moment, yes. This will change on Monday because at the moment we are only calculating efficiencies based on the amount of energy that is extracted, used, and discarded. One aspect that is missing right now is temperature. What are the temperatures of these things? That's not something we can characterize at the moment because we are dealing with processes that are inherently very inefficient. Again, Monday, we're going to learn about something called the Carnot cycle, which is the most efficient engine that one can possibly have. And it turns out that when we look at PV diagrams of Carnot cycles, we can equate the heats that are being exchanged to the temperatures of the reservoirs. And so when it comes to perfectly efficient engines, Carnot engines, something along those lines, we'll have statements for efficiency that involve temperatures as well. So I'll just say that. All right, so let's look at a really simplistic heat engine and analyze it on a PV diagram. This is good stuff here. So this is not the only way that heat engines are done. Just be very clear about this. We are just creating a process that allows analyzing on a PV diagram to be done very easily. So in this process, we are going to have a mass that rests on top of a piston. And we're going to heat up that gas, and we're going to see an isobaric expansion, okay? Constant pressure. Why is it constant pressure? Because the pressure is attained from the weight of the three things on top of our fluid here: piston, mass, atmosphere. That establishes the pressure. So as heat is inputted, that sounds bad. Inputted, transferred to, how about that? That sounds better. We see a volume expansion, right? Now, it's an isobaric process, so as you might remember, you're going directly to the right on your PV diagram. Yes, the volume increases, but you're moving to a new isotherm. You're heating up. And so we reach some final volume where the piston has been lifted up. We're doing work here, right? We're doing work here because we're doing work in our environment right now, right? We lock the piston, take the mass off, and let everything just kind of chill out. Now we have a different process here. Now we reach the second stage of our process, which is a constant volume cooling. Locking the piston does not allow the piston to fall. The volume's set in stone here, and we let heat just escape out. Eventually, enough heat escapes out, we remove the piston, we apply a force down on that piston that will compress the substance while keeping the temperature constant. Okay. So the idea is that we are doing the force in a controlled method to ensure that we have an isothermal process. Again, it doesn't have to be an isothermal process. And it may be difficult to achieve, but it can be done. We'll just say that, right? It can be done. All right. Uh-oh. My goodness, I'm all over the place here. All right. So how is this going to look on a PV diagram? Here we go. We start up here at point 1. Heat is placed into our system in an isobaric process. Once we get to step 2, we have a higher volume, we have a higher temperature. The mass is taken off, we apply the pin, and we let the system cool off. And so we have our QC, where energy is being removed. That's our QC, that's our cold reservoir. It cools off, we drop to a lower isotherm, we drop to a lower pressure, because we took that mass off, and we have a constant volume thing happening now, right? And then the last step is an isothermal process by which we have more heat exchange, but we keep the temperature the same. And it's ultimately a cyclic process. We can see where the heat goes in and where the heat comes out. If you want to calculate the work that's done, you calculate the area bounded by the cycle here, which would also, by the way, be equal to the amount of heat put in to the amount of heat extracted out. They won't be the same. That will be equal to the work. And so you can actually calculate in both ways. You can calculate the area bounded by the cycle here. You could also calculate it if you know the amount of heat that's being put in and taken out, and they're the same. So that's a really simple, really nice way to do that.
Leftover rice without shrimp.
Leftover rice without shrimp.
They all ate the shrimp,
Okay.
and there's just too much rice.
Okay. Well,
and veggies.
can't eat too much on video here. Sorry, everybody. I'm gonna take one bite of rice.
Do you want sriracha or soy?
Well, I'm teaching.
You can eat. Well,
I can't eat when I'm teaching.
They'll think it's fine.
No, they don't want to hear They don't want to hear me
I don't want to hear that.
munching.
either.
Yeah, nobody wants to hear me munching. All right. I'll eat later. Okay, so. All right, so this. Well, she did a good job, to be honest here. All right, so.
What was that? I did what?
Nothing.
A good job.
I don't know. Maybe you did, maybe you didn't. I don't know. Okay. I don't need those carbs. I put on some pounds in this pandemic. I don't need any more carbs. But that rice is good. She did a good job. All right, anyway. All right, so in this process here, we have a more... in this process here, we have all kinds of things that can work. And, in the last example, it probably was a fluid of some kind. Oh my goodness. All right. You know what? I'll sell you some mukbang. That's funny. I've been really watching a lot of mukbang videos recently. It's weird. Mukbang videos, I'm like horrified, and at the same time, I'm like hungry. What's that one guy? Nikocado. We've been watching a lot of Nikocado. What? Don't give you spaghetti. I'm not actually going to feed you. No, I am not going to give anybody food. I'm not going there. That's weird. Anyway. No, but yeah. I'll do a mukbang as I'm teaching physics. That'd be nice. What? Pizza too? I'm going to talk to Jason about this. I don't know about this. Buttering you guys up with food? Not my style. But anyway, my point was we have usually a working substance of some kind. It can be a solid. It can be a liquid. It can be a gas. Well, we are going to primarily focus on gas, though. Why? Because we've already worked out so many details about gases, and gases are so much easier to work with that we can really tackle the fundamentals before we start to deal with more complicated things. So ultimately, whatever it is, we're always going to talk about closed cycles, cyclic processes, and the work can be computed in a lot of different ways, but if you really know a lot of details about your process, then you can find your work from your PV diagrams. Okay? Now, remember this. I'm going to say this a couple times to really get it in your head here. On PV diagrams, if you select a given you select a location on your PV diagram, guess what you can do with that? You can apply the ideal gas law, assuming we're dealing with a gas, right? We always deal with a gas on PV diagrams. You can use your ideal gas law to figure out the static parameters at that instant. Once you start to move through a process, then we apply other rules, right? Work, we can apply heat, right? We can apply both those things mean we can apply the first law of thermodynamics. So again, something that you want to remember, because we're going to be doing this a bit today and probably on the next class too, but static positions are all about ideal gas law. Movement is all about work and heat and first law of thermodynamics. Right? Okay, good. Okay, how much work is done in one cycle? So this is a process here. We got we don't have a starting point, but let's say we start in the bottom left here. We got something going up and to the right. That's an unknown process. Then we have an isochoric process followed by an isobaric process. But what's nice about the unknown process is that it has a relationship between the pressure and the volume that makes the work very easy to figure out. So why don't you tell me and pick a letter and let me know how much work was done here. You know, if I was in class, I'd serve you guys steak just to one-up Bowen. Pizza, spaghetti, steak. Straight up buy steaks for everybody. And let's see what he has to perform then, huh? All right, a lot of B. I like B. It's wrong. It's wrong though. All right. Remember, you're doing areas here, right? Doing areas. That's true. Omaha Steak does deliver. That is true. Anyway, so either it's an area of a triangle, right? 1/2 base times height. What's our base? 2. So 1/2 of 2 is 1. What's our height? 2,000. Right. So we got C. Why did you all say B? I just assumed it was B. I wasn't even looking at my own question. I don't know. Sometimes I get tripped up that way. All of my students are saying C. I mean, they're all saying B. I'm such an amazing teacher. Of course it's B. Oops, it's not. Oh yeah. Yep. No, I get it. Okay. Now, we are given some extra information here. We know that the area is 2,000 joules, which is the amount of work being done. Say we know that in the process of going from point A to point B, and that's this unknown process here. What happens in that process is the volume increases, the pressure increases, and the temperature goes up. And in that process, we would be inserting a lot of heat. Yes, you're doing work, but you're going to have to put in some heat to make that temperature go up. And say we're told that 500 joules of energy are put in as the heat reservoir. Well, how much would be exhausted to the cold reservoir then? Let me know what you think about that. All right, well, I'm not going to keep you in suspense. It's pretty clear here. The answer is C, 3,000. Now, where is that coming from? Well, it can come from a lot of different places. I mean, technically, it can be part of either of the two branches. There has to be some QC in both, though, because if there's 0 in a branch, that's a adiabatic process. And we know how adiabats look. They look similar to isotherms. They're not exactly isotherms. Remember, they have a steeper slope to them. But we don't have anything like that here. In the isochoric process, we are lowering the temperature because we're going down on the PV diagram. And in the isobaric process, we are moving to the left, which means we're also going down in temperature. So it's safe to assume here, it's not really an assumption to be honest, that there is heat being extracted, exhausted out in both of these processes here. All right. Which of these heat engines has the larger efficiency? Look at both of these and let me know what you think has the larger efficiency. I mean, one thing that's obvious when you look at it, right, the amount of work being done is totally different, right? So keep that in mind. It's not D. Let me just tell you, it's not D. And if you don't remember, in our PV diagrams, almost always we have to keep our amount of gas constant, because in the ideal gas law we have 4 variables: P, V, N, and T. And in a 2-dimensional diagram, you can only really have 3 things change. If you have a fourth thing that changes, I mean, you have to either display that three-dimensionally, which would look wild. It'd be very hard to visualize that stuff. Or you'd have to create multiple PV diagrams, which is just a headache. So, I mean, it could be done, but it's just not something you really want to do. All right, what do we got here? A lot of A. I'm liking A. Great. So, here's what's going on. The process in engine 2, where the temperature goes up in both of the isochoric cycle going up and the isobaric cycle going to the right, those are both increases in temperatures. We're getting heat from a hot reservoir there. That's the same. That's the same. So QH is the same here. But there's more work being done in engine 1 because there's a greater area bound. Right? So that's a more efficient engine there. Okay, that's a more efficient engine. Okay, now, again, let me just specify one thing here. We don't have a lot of details. What exactly is happening in these processes here? I mean, it may be possible that engine 2, from a mechanical standpoint, an engineering standpoint, a practical standpoint, is just a much better thing to make. Easier, whatever. If you can manage engine 1, clearly it's more efficient. But see, this is the big difference between physics and engineering. Physics tells you what you can do, and engineering is what you actually do. Okay, physics is in the clouds in some ways, and the engineers tell us what is practical and reasonable, and then you have to worry about costs and all those things. You future engineers, I appreciate you, but I like my head in the clouds. Okay. Basically, if it doesn't involve duct tape, I'm not much of an engineer, put it that way. Okay. So let's do a couple examples here. Now, from the looks of it, I am not going to get through these lecture slides. That's okay. I'm going to keep you here, though, until as long as I'm allowed to. And what I will probably do is this. When I re-record the previous lecture, not looking forward to that, but I guess I got to do it. When I re-record the previous lecture, I will lecture on the rest of the stuff, and it will go up as part of the video tomorrow. I'll put out an announcement about it later as well. Anyway, let's look at these, at least these two examples. I will get through these, and I'll get a little bit into how a car engine works. So let's jump to those examples right now. Okay, there's a lot going on in this problem, so buckle up here. We got a PV diagram, all right, of a heat engine. Okay, this involves we start at point A, and we have a iso. Oh, it's an adiabatic process actually. Okay, so A to B is apparently an adiabatic process, no heat transfer. B to C is an isobaric process. That's the cold reservoir aspect of it. That's where heat is extracted out. And C to A is an isochoric process. That's where the heat is being put in. Okay, fine. We have an ideal gas with a adiabatic constant of 1.4. So we are dealing with effectively air, right? Because the adiabatic 1.4 value is it's basically for air. So that's true of any diatomic gas. The monatomic gas would have a 1.67 is what we said. So if you're not told your gamma value for your adiabatic process, you would know it based on what the working substance is. If it's air, that's, I was going to say diabolic, but it's not diabolic, it's diatomic. I don't know what I was thinking. But it's diatomic, and that's 1.4 for your gamma value. All right, so what we want to do here is we have our working substance. It's air. It's 2.5 moles. We're told that cycle AB, or the process AB is adiabatic, and we want to go ahead and start finding a bunch of information here. So what's the best thing to do here is to go through each process and try to figure out all the missing variables. Because like I said, for A and B and C, you can do an ideal gas law here that analyzes what the parameters are at these locations. When it comes to processes, there are equations that we use for the different processes. So we have both things to work with here. All right, so in the first step, we want to do our adiabatic process. So it's a little hard to see here, but, and I'll try to zoom in a bit so you can see this more. Shouldn't I get a little zoom in feature here? Oh, it's right there. Okay. So we are told the following information. We have the volume at A and C and the volume at B. So we have the volume at all different parts here. We are told the pressure at C and B. We do not know the pressure at A. We want to figure that out first. So A to B is an adiabatic process, and if you remember, there are a couple different relationships for adiabatic processes, one of which is a relationship between P and V. The other one is between, well, there's technically three. There's a PV relationship, a PT relationship, and there can be a VT relationship. Well, we want the PV relationship, so it's PV to the gamma power, PV to the gamma power. One side of the equation is for A, one side of the equation is for B. We have that information. We put in our pressures. We're using atmospheres here. You might say, well, shouldn't you be using Pascal? In ideal gas law, you do. When it comes to proportions or ratios, the units cancel out ultimately. And so you don't have to convert to Pascals in this situation. We can keep things in atmospheres, and we are going to keep things in atmospheres. So I do my adiabatic relationship here. We end up with a higher pressure at 12.3 atmospheres. Fantastic. Okay. Now, how much heat enters this gas per cycle, and when does it happen? It can only happen from process C to A, the isochoric process, right? It can't happen on A to B, that's adiabatic. And on B to C, the temperature's dropping. So that's not heat entering, that's heat leaving. In an isochoric process, there is no work being done. So our first law of thermodynamics says that E thermal equals the heat, which would be QH in this situation. We have a diatomic gas. E thermal is 5/2 nRT. That's for diatomic gases. Now, I don't have my temperature or my, well, I have my moles, but I don't have my temperature. So one thing you can do here is, now this is a delta T. I'm sorry, in the example here, this T should be a delta T because this is a delta E thermal. Anyway, so in the isochoric process, I can replace, using the ideal gas law, my nRT to a delta PV. P changes, V does not. That's why the delta P is there. And I have all this information. 5/2 go in here. 5/2 go in here. I feel like I gotta use my calculator, gigs. It looks like my 2 is gone. Where's my 2? Let me just make sure it still works out. It's weird. 0.13 to the 5th. 0.002. Syntax error, come on. Give me no syntax error. Alright, it's my fault. Okay, my goodness, I'm a wreck right now. There's a 2 here. It's 5/2. I didn't write it for some weird reason, but anyway, that's this amount of heat right here, 5.47 kilojoules, that's correct. All right, let's jump to the isobaric process. That's part C. How much heat leaves the cycle? So what happens in an isobaric process? In an isobaric process, we use our first law of thermodynamics. There is work being done, right? We can calculate that work being done. I mean, you can calculate the area here if you want. That's a good way to do it. E thermal is, it's given by NCV delta T. Now that CV, that's where the 5/2 R come into play. Those are the same things, right? So let's go ahead and put our numbers in for that. Let me scroll down a little bit here. I'm going to move the work over to the other side. I got NCV delta T plus W equals QC. Let's put in our numbers here. So I replace the N delta T using the ideal gas law because I don't have any information about temperature. So I'm going to be using my ideal gas law repeatedly to switch things over to pressure and volume, right? So the N delta T turn into P delta V over R, the delta V because our delta V is changing, and now we're going to add all this up. If I add all this up, I get this. Now, by the way, if you remember back in a couple lectures ago, we talked about two different values of specific heats for gas: constant volume, constant pressure process. In a constant pressure process, there's extra work being done, so your CP value is a little bit bigger. Actually, it's bigger by a factor, not a factor, by R. But you don't need to do that. You don't need to do that. So anyway, I got CV plus R over R. So that ends up being 7/2 when you do the math here, because this is already 5/2, and you add 1 to it. That's why you get the 7/2. We put in all the numbers in there, the delta V, and we get a minus 3.72 kilojoules. Now it's minus because QC is energy extracted out, and the difference in volumes do end up with a negative quantity. You can certainly keep it positive just for as an absolute value, just to know the magnitude of that heat. But again, you could also leave it as negative. When we want to calculate the work being done, it's very easy to do that because we simply have to take the difference between the hot and the cold reservoirs, and we get 1.75 kilojoules. Doing work in an adiabatic process is a little complicated, and that's why it's nice that we have these concepts here, because it allows us to do this work much easier. The thermal efficiency of the engine is going to be the work over the hot reservoir. So that's the 1.75 divided by 5.47, and we get an efficiency of around 32%. Not too shabby. So this is a fantastic problem. Fantastic problem. And here's what I recommend to you. Again, I'm gonna process this video. It's gonna go back up. I recommend you watch this again. Go over it repeatedly. Make sure you understand every aspect of it. This problem lies really at the core of this whole chapter. We use our knowledge of PV diagrams. We use our knowledge of thermodynamic processes. We use our knowledge of the first law of thermodynamics to analyze a cycle of an engine. And we can get all the relevant information that we want out of it. We don't have information about temperature, but guess what? I can apply my ideal gas law at any location here and get my temperatures. That's an option. That was something I could have done here, by the way. You notice that in a lot of these situations, I said, oh, we got NRT. Let's just make that PV, right? I mean, I didn't have to do that. I could have solved for temperature in all these different situations. It would have been a little bit more of a nightmare, honestly. That's why I didn't do it. It should be a lot more steps, but fantastic problem. So before I move on, let me ask you, is there anything about this that was not clear? Do you have a question for me about this absolutely stellar problem?
Not yet, but we could ask an office hour.
Okay,
right?
that is the correct response.
Okay.
That's the correct response. Not yet. That's good. I'll tell you what. You're not going to see this problem and hear me yada, yada, yada for 10 minutes and be like, yeah, duh. No. You got to sit there and you got to think about it for a long time. And then it will hopefully sink in. But this is an excellent problem. This really encompasses a lot of the last chapter and this chapter. And if you don't think a question like this is going to be on your test, well, you're wrong. There's absolutely a question like this on your test. Maybe more than one. I don't know. I haven't made your test. I'm going to make it over the weekend. Can't wait. I'm excited. I love making tests. Love it. All right. So let's let me do this in-class activity. This is, again, normally if we're sitting in class, I have you sit down and do this, and this is normally when I take a break, but I spent too much time talking about the exam, so I didn't get to this in time. But anyway, let's just go over it now. A gasoline truck takes in a gasoline truck engine takes in 10,000 joules and delivers 2,000 joules of mechanical work per cycle. All right. QH is 10,000, work is 2,000, QC is 8,000. The heat obtained by burning gasoline with the heat of combustion is 5 times 10 to the 4 joules per gram. What is the thermal efficiency of this engine? Well, that's easy, 20%, right? Work over QH, 20%, easy. What is the heat discarded? I put it as negative 8,000 joules. If you just said 8,000 joules, it's acceptable. The negative is not that important. All right. If the engine goes through 25 cycles per second, what is the power output in watts? Okay, remember, watts is joules per second. So each cycle is 2,000 joules. And if you have 25 cycles per second, that means one cycle takes place in 0.04 seconds. So we do 2,000 over 0.04 seconds, we get 50,000 kilowatts. The other way you could have done this is simply multiplied the 2,000 by 25. That would work too. You could just figure out, okay, well, if each cycle is 2,000, 25 times 2,000 is 50,000, so that you can do that. That works too. How much gasoline is burned in each cycle? This is a latent heat problem, right? Latent heat, where we're taking our liquid and converting it into a gas. And so we want to work out for the amount of heat that it takes in, how much mass is actually being burned here. So we take our 10,000, sorry, the units here, it says 10,000 joules per gram. It's just joules. I don't know why it says joules per gram. 10,000 joules, that's in one cycle. The heat of combustion is 5 times 10 to the 4. So we end up with 0.2 grams. So every cycle, 0.2 grams of fuel are being used, okay? In fact, you really start with the heat of combustion. 0.2 grams are being combusted, and when you multiply that by the latent heat of vaporization for this gasoline, that's how we get to 10,000. And so now remember, that's one cycle, but this happens 25 times per second. So that means it's either 0.2 grams per cycle, or 5 grams per second, or 18 kilograms per hour. Okay. So you could work out, if you know the size of your tank, how long this engine could run with the efficiency that we have. So that's a nice example. Very nice example, actually. Any questions about this one? Can you tell Junior to not act like he's...
Hey, Junior.
Junior, calm down, man. All right. All right. Questions? No. All right, let's move on. Uh-oh. I don't think that's right. Try this again. That's correct. Okay, so. All right. Here's a more realistic example. This is your standard automobile engine. It's different than a diesel engine. Diesel engines don't have one of these steps. I think diesel engines don't. If I remember correctly, I don't think diesels have spark plugs. Right? Is that right? I don't think they have spark plugs. So what happens is the compression of the... Okay, let me just talk about this before I start talking about other engines. But please correct me if I'm wrong here. Like I said, I don't know much about cars. I don't really like cars too much. Okay, Barton, thank you very much. What happens here is the intake valve's open. Aerated gasoline is placed into the cylinder. The crankshaft does a compression, right? We have a compression. And I think with the diesel engine, the compression is sufficient to ignite the gas. In a standard automobile, the spark plug does that. Again, I don't know anything about that. I should probably learn about that. Wonder why that's like that. I don't know. Anyway, so the spark plug fires, right? That's the ignition. So that's our QH, right? And we have a rapid expansion. So it makes this crankshaft keep going. And the exhaust valve opens up. So everything's got to be timed right here. You have timing in this engine that makes sure all this cycle happens at the appropriate time. And the exhaust comes out. So there's a lot of processes happening here. Let's analyze what goes on in these processes, though, from the thermodynamic standpoint. So this is a pretty simplified example of what's happening here, but it's very close to reality, actually. We start with A, okay? And at A, we first have this adiabatic compression. Now, it's adiabatic, and what I mean by that is, you obviously know what adiabatic means, right? Adiabatic means there's no heat put in or heat put out. And I mentioned this a lecture or two ago, and but it's because the compression is rapid. It's very fast. And any fast process, thermodynamically, is adiabatic because there is time, right, that has to, where energy flows. So if heat's going to flow in or out, that takes time. If you do a process very rapidly, it is inherently adiabatic because there is no time for heat to flow in or out. So the compression stroke is an adiabatic process. Boom, we go up at a higher temperature now, right? The compression of the gas, we lower the volume, pressure goes up, temperature goes up a little bit actually, and then boom, we ignite the gas through the spark plug. And that's our QH. So all of a sudden we're putting a ton of energy from the combustion. And it's and then what happens there, again, it's very quick. The volume doesn't change, so it's an isochoric process. Pressure jumps up because the temperature jumps up. So we're at a higher isotherm now. Great. Now, as a result of all that energy being released, we have adiabatic expansion. It's a very rapid expansion as the cylinder, as the piston expands in the cylinder. And we have an adiabatic expansion because it's very rapid. And so we see that our temperature goes down a bit, pressure goes down, volume goes up, obviously. And then we have the exhaust. And that's, the piston has been, completely open now. The intake valve, the outtake valve is open. Exhaust is going out. That's isochoric. There's no change in the volume there. And then the process starts over again. The amount of work that's being done is bounded by the graph here. We know how much QH is being put in. The in-class activity that we just did, the last example, kind of explains that. We look at the latent heat of vaporization for the gasoline. We know exactly how much energy is going to be put out there. We know the amount of work that's going to be done in that process. So, in the most simplistic way I could describe it to you, this is our basic internal combustion engine. So, combination of a lot of isochrotic processes and adiabatic processes. This is ideal, obviously. But the deviation is not too dramatic for what we have here. So, right, let's move on. All right, so let's look a little bit about refrigerators. This is the opposite process here. Instead of taking heat from a hot reservoir, performing work and discarding it to a cold reservoir, we're trying to do sort of the opposite here. The idea is that we want to extract heat out of a cold reservoir, okay? And through work, we can push that out to a hot reservoir. This is fully allowed by the second law of thermodynamics. Perfectly fine to do this. In fact, you do have a spontaneous, this can happen spontaneously, but the issue is for something like a basic refrigerator, this is not usually a very efficient thing unless you are controlling this in some way. So we're looking at a heat engine basically in reverse here. And so our relationships are a little bit different. Okay, so you do need to be mindful of whether you're talking about a heat engine or a refrigerator. Now, when I say refrigerator, I don't literally mean the refrigerator in your house. I mean a process by which energy is taken from a cold reservoir, work is done, and it's discarded to a hot reservoir. That is how a refrigerator works, but there are a lot of other systems that do that. Your basic, air conditioner is the same way. Your air conditioner is a refrigerator, right? So, but in that process there, you're going to add the cold and the work being put, and that equals the hot process there. Okay, the hot intake or exhaust. All right, so to talk about refrigeration, we have a slightly different concept for efficiency because what we are interested in is how much heat can you take out based on the amount of work. So the focus is a little bit different here. We're actually interested in QC over W. And that is going to be our performance for the refrigerator. We use a capital K. It's like an efficiency. However, this number is bigger than 1 as opposed to the efficiency for heat engines being less than 1, because the idea here is that how much heat are we extracting per input of energy? And the greater value of K you can have, the more you can say efficient your refrigerator is. If you put a little bit amount of work in and you could extract a lot of energy out of your system, that's a good performance. So it's a slightly different way to think about efficiency, and this is how the convention is for refrigerators or anything that operates in this manner here. So here's how your basic refrigerator is going to look. So your basic refrigerator is going to look like this. You have inside the refrigerator, you have your, if you look in the back of it, for example, or actually it's kind of on the inside, really. It's on the inside, sort of attached in thermal contact with the contents of your fridge. You have very cold gas that goes through. That cold gas goes through due to a special sort of, it's not a gasket, but it's sort of a device in the expansion valve that allows the condenser fluid, the compressed fluid, to expand. And the expansion of that fluid will allow the temperature to drop. It drops lower than what's in the fridge. So you can extract heat by being in thermal contact with that fluid. Then it's brought in, once it passes through all the chambers in the refrigerator, then it's brought over to the compressor. The compressor takes all that fluid and returns it to a higher pressure, and that raises the temperature of it. Okay, so we're compressing that fluid, the temperature goes up, and then usually on the back of your fridge is where, or sometimes on the bottom, actually, usually on mine it's the bottom, because all this hot air comes out the bottom. But on the bottom of the back, you have the hotter gas now in contact. That gives off a bunch of heat, so that's your QH there. And then it goes back into the expansion valve, where it's expanded again, it drops in temperature dramatically, heat's extracted out, and this process happens over and over and over again. The work that's being done is in the compressor. It does work on the fluid to compress it, to bring it to a higher pressure that will raise the temperature of it, and then the temperature can be extracted out. The heat can be extracted out. The expansion occurs, it's brought to a lower temperature, it takes the heat out, and this process keeps going. So the work being done is in the compressor. The QH is on the coils or on the back or the bottom of your fridge, and then the QC is the heat that's extracted out the refrigerator. So that is probably the most basic explanation you can get for how a refrigerator works. There's little nuances here and there, but that's the general principle. And it all really boils down to, that's not a pun, it's not anything really, but this compressor here and the expansion valve. This process back and forth allows things to heat up, cool down, you extract heat, heat comes out, you expand it, you cool again, so that whole process continues. Okay, fantastic. All right, so question for you here. I'm going to give you a minute to think about this. I'm going to step away just for one quick minute, but read over this and put a letter in the chat. All right, QC, yep. That's right. So what we have here is we have our QC here of 60. We have the work here. So it's a ratio of 60 to 40. QC over the work being done. 1.5 is the coefficient of performance here. So what we're able to do here is for 40 joules of work, we could take 60 joules out per cycle. And of course, if you can drive up that coefficient of performance, what that means is for the amount of work you do, you're extracting out more energy from your cold reservoir, which obviously, if you can do, you can do. So that's nice. All right. All right, we're going to wrap up the last of the September 9th lecture. Just a couple more problems to do and a little bit to explain about, second law statements. So we have a freezer as a coefficient of performance of 2.4. Right, so that coefficient of performance is the cold reservoir divided by work that's being done. The freezer is to convert 1.8 kilograms of water at 25 C, and we're trying to turn that into ice at -5 in 1 hour. One amount of heat must be removed from the water to convert it. All right, so that is a specific heat problem. Okay, so you see in part A down here, there's 3 parts to that. You have to cool the water down to 0, then you have to freeze it, and once it's frozen, then you bring it down to -5. It happens in these steps. So I have my values for specific heat for water up here, 4186. My one for ice, I use the 2100. You'll see this one's a little bit lower. I think your textbook is like 2060, but I'm sticking with this one here. And then of course 334 kilojoules per kilogram is for the latent heat. So everything has the mass in it. Specific heat times the temperature difference. This is just the latent heat here, and this is specific heat times temperature difference. All right. So technically this is all negative, right? So we got 808 kilojoules need to be removed. It's technically negative, but our coefficient of performance stuff is, it's a positive value there. So, okay, how much electrical energy is consumed by the freezer during this hour? All right, so the cold reservoir is this. That's the 808. So, given that our coefficient of performance is 2.4, we want to calculate the work that's being done here, and we need to do 337 kilojoules of work in order for this process to take place. So if we're trying to do this transfer here, in order to remove that much based on what our freezer is able to do, right? Our freezer is able to extract this energy out, but it needs 331 kilojoules to do that. How much heat is wasted is rejected to the room in which the freezer sits. All right, so we base this on our statements of relationship between the hot and cold reservoirs and work. QH plus QC equals W. We'll work out the QH here, and we are adding these things up. All right, so it's a minus QC, but remember this is technically negative here, and so that's how much. That's how many joules of heat is wasted. So there's work being performed, right? And in the refrigeration process, that work's typically done to compress the gas, right? You're doing work on the gas to do that. And then it's eventually brought back through where it can expand and then get to that lower temperature. But this is how much heat's got to be rejected in order to perform this amount of work, right? So if we look back at our relationship here for refrigerators, I mean freezers are refrigerators, right? The same thing. If we look back at that basic energy process here, that's what we're looking at here. So the QC is how much energy we're taking out from that freezer. We have work coming in, and that's all being expelled to the hot reservoir. Okay, so the work comes in many forms, but ultimately that's the relationship we're dealing with here. Right. Now, in this problem here, QC is it was negative here, so
the convention here is we moved it over and just realized that you add these things up. Because look, what goes in here, what goes in here, that comes out. All right, so let's look at last few things here. All right, so in this particular lecture here, we have developed a lot of different statements of the second law of thermodynamics. Because as I mentioned, the formal statement involves entropy, which is what we're going to get into in the next lecture. But a more practical side of the second law of thermodynamics looks at individual situations. So the statement that you see in the middle here is the engine statement. You can't have a process that can take heat and turn it completely into mechanical work. You have to have some exhaust. You have to have some waste there. And that's a statement of second law. There's no way you can just take pure heat and do pure work out of it. The refrigeration process it effectively is the same message, but it's just packaged for that particular application. But you cannot just take heat out of a cooler system and move it to a hotter body without doing work in the process. A refrigerator just doesn't work by itself. You have to have a process that can perform work to basically push that energy through. So, and here are the sort of visual versions of these laws. So, it's impossible. The heat engine on the right here, again, can't do this. You can't decide to take heat out of a hot reservoir and have it be 100% efficient and it does work. Something has to be expelled down to here. In fact, the thing on the right, it kind of shows by contradiction why this doesn't make any sense. Because if you had a refrigerator that didn't do work, where you could just naturally just have things flow to a hot reservoir, then you could use it with a heat engine to create 100% efficient energy. All right, because what happens here, look, if you look down here, these diagrams, these arrows and the thickness of this stuff is meant to be, somewhat proportional to the amount. So if you are extracting heat out here, and then you have a heat engine where that same amount of heat's being put back in, well, this adds up to 0, right? And then you effectively have this. So this is impossible, the refrigerator, without work, and this is impossible without the coal reservoir. Okay, so that's the practical side of that. And we're going to look at the more formal definition in the next chapter where it involves entropy, but entropy is an odd concept. Unfortunately, because we have this class that's a hodgepodge of topics, we don't really get into entropy in any meaningful depth. You just know it exists, and it's something that exists. I guess I'll just say that. Here's another view of this. These two, these are really the same statements here. So you have if you just basically reverse this process here, what you're saying here is I'm going to take 100% efficient energy, and that's going to be the work that's done for my refrigeration. Well, okay, you're taking energy out of the hot reservoir and then you're putting it back in. Well, it's like you have nothing there. So you're just really, these two branches over here just disappear and you end up with this. Again, not possible. So these are, say I'm going to have a workless refrigerator do a heat engine for me. Well, that's equivalent to the thing on the right. No. And then this is the other statement where it's like, well, let's have that heat engine perform this work for our refrigerator. No, can't have that either. Not happening. All right, let's do one last question here. A problem, and then we will be done with this. Okay, so in-class activity. Again, this is something you would work out, so this is relatively easier. But we have a refrigerator with a coefficient of performance of 2.1. And remember, that's your QC over W. Each cycle absorbs 3.42 times 10 to the 4th joules. That's our QC then. How much mechanical energy is required each cycle to operate the refrigerator? Well, that's pretty straightforward. We use our coefficient of performance equation there. So I'm going to rearrange that to QC over K. And so the QC over K turns out to be 1.62 times 10 to the 4 joules. So you combine those together, because remember what you're doing here is you're putting this work in, you're taking out the QC, and both of these things are what is brought to the hot reservoir. If we look at the simplistic, the diagram, energy diagram for this. So, the equation that we have here, that QH equals minus QC plus W, I have that in there like that because I don't like to put negatives on my QCs. So I have it originally like this, and when I put it like this, you can see, this is energy being extracted out. So anyway, so if, you would have this as negative though, and the idea is that you add these up. Okay, you add these up. In fact, it probably would be better to put the negative over here, I guess, but just different conventions. So we add these up, we get 504 kilojoules. So with this refrigerator, with the performance that it has, it can take out this much energy. It requires this much work to be done, and then overall we're expelling 504 kilojoules of this. All right, so that takes us to the end of this, and